Okay. Welcome, everyone. It's nice to see you here, and it's very nice to see Terry Hughes here. Professor Terry Hughes from Townsville, from the Australian Research Council, Center of Excellence of Coral Reef Studies. Terry is, as some of you knew, and a really superb person in understanding the oceans and coastal and marine systems, and especially coral reefs. So we're looking really much forward to your talk today. It's great to have you here, Terry. Welcome.
Hi, everyone. It's a great pleasure to be back in Stockholm again and enjoying Carl Folke's tremendous hospitality. I've prepared, I think, quite a busy talk, so I'm going to launch straight into it. Carl has given me several hours' notice to prepare this talk, so I've spent the morning being quite busy getting it ready. I'll explain what gilded traps are in the last section of the talk, but basically I'm going to talk about resilience, phase shifts, and the role of fisheries in the dynamics of marine ecosystems. So I'll start off by talking about phase shifts in a marine context and the resilience of marine ecosystems. I'll be talking a bit about trophic cascades, particularly top-down effects of overfishing and the loss of biodiversity on the resilience of marine ecosystems. And towards the end, I'll talk about whether or not we can anticipate ecological surprises, knowing what we know now about some systems that have undergone phase shifts. So what do I mean by resilience? Resilience is defined as the capacity of a system to absorb insults or disturbances without fundamentally changing into something completely different. And the system can be ecological, or it can be socioeconomic, or it can be both. So you can think of a transition from a reef that's dominated by corals in the tropics to one that's dominated by seaweed as an ecological phase shift. But equally, we could think of the Wall Street crash or the French Revolution as a phase shift in the social and economic domains. These alternative states might be deemed by societies to be desirable or undesirable. That's not necessarily a universal value judgment, which raises all sorts of issues about equity and empowerment. I'm going to deal with the ecological consequences, however. But it's important to realize that resilience may not necessarily be something you want. If you're in a state that you don't like, your goal as a manager might actually be to erode resilience of the bad place and move to somewhere else. And I think we could refer to a resilient bad place as a trap, somewhere that's hard to get out of. So a couple of examples in the marine context of ecological regime shifts include coral reefs. I'll talk a little bit more detail about the Jamaican case study, which is probably one of the best understood marine regime shifts. We are also seeing increasingly regime shifts in the pelagic realm that can either be top-down impacts of overfishing or bottom-up impacts of nutrient addition or climate change. Another familiar example in temperate systems is the transition between lush kelp beds, which are highly diverse and three-dimensional, into so-called sea urchin barrens, where high densities of grazing sea urchins remove the canopy of the kelp and result in a very different system. So in the talk today, I'm going to talk in some detail about three different case studies that have some interesting differences in their social and economic settings. So I'll start off by talking about the Jamaican phase shift. Jamaica is a developing country in the Caribbean, and the main human coral reef interaction in that context is subsistence and artisanal fishing. I'll talk then about the Great Barrier Reef, which is very different socioeconomically in that Australia is one of the very few tropical countries with extensive coral reefs that happens to be a wealthy country. And so the main economic interest in the Great Barrier Reef is tourism. There's a much smaller economic interest in recreational and commercial fishing. And I'll talk also in the context of regime shifts about shifts in land use and the type of coastal agriculture and its impact on the Great Barrier Reef. Just to put some numbers on that, tourism on the Great Barrier Reef is worth about $4.5 billion a year to the Australian economy, and it provides employment directly and indirectly for 68,000 people. And the final case study I'll talk about today, and I'll develop the concept of gilded traps, is the Gulf of Maine. And the Gulf of Maine has very heavy commercial fishing for a long time, and another important social and economic phenomenon that I'll refer to is sea change. I'm not sure how well that translates into Swedish, but it means people moving to the coast, buying summer homes, often taking early retirement, and people refer to that as gentrification. One way to envisage phase shifts is to use what's called a stability landscape, which is made up of hills and valleys. And we can consider the state of the ecosystem to be represented by the ball rolling around the landscape. And the valleys represent alternative stable configurations where the ball may come to rest, and the hills represent thresholds where the ball is unstable and it can either go in one direction or another. We can think of the resilience of these two alternate states as being represented by the depth of the valleys. And we can intervene through human influence to either erode resilience or build resilience. So, for example, a common transition on coral reefs is from a healthy coral-dominated state to a less desirable state dominated by fleshy seaweed. This is a picture from the inner part of the Great Barrier Reef, parts of which have undergone this transition to dominance by macroalgae. That shift was promoted by a buildup of added nutrients from runoff from land, and also in some places due to overfishing of herbivorous fish. So the recipe for making this transition happen for a coral reef is quite simple. You take away the lawnmowers that control the macroalgae, that's fish species like parrotfish and surgeonfish. You fertilize the reef by adding nutrients. Then if you hang around and wait for something bad to happen to corals, and increasingly these days that's likely to be coral bleaching from climate change, instead of the corals recovering after that mortality event, they are likely to be replaced by faster growing fleshy seaweed. Once that transition takes place, it locks in because this algae is very thick and it's virtually impossible for a juvenile coral to come out of the plankton after its dispersal phase and settle onto the substrate, because it would be impenetrable, and if it did make it to the substrate, it would have a high mortality from being overgrown and smothered. So that's basically a concept diagram that I'll come back to towards the end of the talk to illustrate regime shifts in the marine environment. Another set of dynamics to consider in terms of regime shifts is the structure of food webs. This is a somewhat idealized food web for a coral reef. And I'm sure you're familiar with these things. The top layer are the top predators. Then we get a secondary layer of predators, herbivores further down, and at the bottom, so-called primary producers, which get their energy generally from sunlight. These arrows represent the flow of energy or nutrients, who eats whom, basically. And an ecologist can go in the field. They can measure food preference and diet and consumption rates and so on. And we can quantify that. It still amazes me to this day how many published versions of food webs there are without one very important species in them, namely people. And in fact, this is what most food webs for coral reefs look like today. They are highly altered, particularly in areas with heavy subsistence fishing. So I'll talk a bit about so-called top-down impacts, which is what happens to the structure of the food web when species higher up in the food chain are removed. And increasingly around the world, we're seeing a phenomenon referred to as fishing down the food chain, where top predators have long since been removed. And now, particularly in coral reefs, the main focus of fisheries is on herbivorous fish. Those fish are functionally very important in terms of the resilience of a reef, and overfishing of herbivores, as I mentioned earlier, is critically important for eroding resilience and promoting a phase shift to dominance by algae. The opposite of top-down effects is so-called bottom-up effects, which is what happens when you fertilize a reef, when you add nutrients. That promotes primary producers, and so we can get a mirror image of top-down effects occurring from the bottom up by adding nutrients. So an algal bloom tends to promote herbivores and so on upwards through the food chain. Okay, I want to move on now and talk about the three case studies that I've selected. And I'll begin by talking about some work I've done over a long period of time in the Caribbean island of Jamaica. This is a photograph I took in 1979. I was only about 4 years old, I think. It was a long time ago. Actually, I think I was 21. But at that time, this was a beautiful coral reef. Coral cover, which is the standard metric of health of a coral reef, it's what people monitor, was very high. Often it was 70 or 80%, which is what it is roughly in this picture. This is fairly shallow water, about 5 meters deep. And we can see here two very abundant species of corals called Acropora palmata and Acropora cervicornis. Those two species were the dominant corals on Caribbean reefs when I began to study them in the late 1970s. And they had been described in the earlier studies in the 50s and 60s, where people went out and described for the first time the depth zonation patterns of Caribbean reefs. So these zones extended parallel to the shore for tens of kilometers in both directions. What you can't see in this photograph is any fish. And the reason for that is because of chronic subsistence fishing, which had depleted the biomass of fish on Jamaican coral reefs by roughly 90%. The top predators had long since been removed when I started studying there, and so most of the fishing was subsistence fishing that targeted parrotfish. Now, parrotfish are ecologically very important because of their grazing activities, and these are some parrotfish scrapes. So even to this day, if you order fish in a Jamaican restaurant, you're likely to be served 5 or 6 parrotfish this size that are deep fried so that you can eat them bones and all. And that, I think, reflects the state of the fishery and the biomass of fish on this reef. As a consequence of the removal of predatory fish and herbivorous fish, there was a trophic cascade, a top-down effect that influenced this species of herbivorous sea urchin. This species, in the absence of its predators and other herbivore competitors, parrotfish and surgeonfish, had increased in abundance to extraordinarily high levels. Typical density of these things was about 10 per square meter at a depth of 5 to 10 meters or so. It was more than that in shallow water. The highest recorded average density of diadema in Jamaica was in 1976, and it was an average of 77 diadema per square meter. Now, at those sorts of densities, that abundance of diadema is not actually sustainable, because diadema, as well as being an important grazer, is also a bioeroder. Its grazing activities, which remove the algae, also create sand. And when you get densities above about 3 or 4 per square meter, diadema will actually remove more calcium carbonate from a reef than the reef can accrete through the growth of corals and other calcifying organisms. So that's the first example I'll show you of many of a trophic cascade that's related to the intensity of fishing. In 1980, a big hurricane occurred. It was a Category 5 hurricane called Hurricane Allen, and it destroyed most of the Acropora palmata and Acropora cervicornis corals in shallow water on the reef. Other corals that were less susceptible to the cyclone didn't do as badly, but this was a major disturbance. Now, corals are adapted to coping with recurrent cyclones. They've dealt with them for millions of years. But this was a hurricane that had a long-lasting impact. So if we look at percent cover of corals through time, this is what the first photograph I showed you looked like, about 70% coral cover. The cyclone or hurricane in 1980 caused a drop of about half of the cover. Then we began to see the beginnings of a recovery for a couple of years afterwards. And then, beginning in 1983, we saw a sustained decline of corals on Jamaican reefs, and they have never really recovered. So what has happened here, that the reef has lost its resilience, that it's lost its capacity to absorb yet another hurricane, and instead of recovering, it has undergone a phase shift to dominance by seaweed. The reason that phase shift occurred was because of a die-off of diadema. By the time the hurricane struck in 1980, diadema was the sole remaining abundant herbivore, because herbivorous fishes were very strongly overfished. The density of diadema was exceptionally high. It was hyperabundant. And those sorts of conditions are precisely the conditions that favor spread of diseases through an artificially elevated population. Any monoculture, including crops and aquaculture, are very susceptible to the spread of diseases because of their unnaturally high population densities. So the last remaining herbivore in this system died at a rate of 99% in 1983. This is what the reef looked like just before the die-off of diadema. I forgot to tell you its common name, which isn't terribly imaginative. It's called the long-spined black sea urchin. Anyway, this is what the reef looked like shortly after Hurricane Allen, but before the die-off of diadema. So there's quite a lot of bare space. This is Acropora cervicornis rubble that was created by Hurricane Allen. There's virtually no large macroalgae in this picture, because as soon as they poke their head above the substrate, a diadema will graze it. Diadema are performing an important ecological function here as the sole remaining herbivore. They're keeping the substrate clear so that juvenile corals have somewhere to settle without being outcompeted by algae. Then the unimaginable happened. Diadema all died, and we ended up with this very rapid phase shift to macroalgae. Now, the trajectory I showed you earlier, if I can get back to it, varies from place to place around the Caribbean, because not all reefs within the Caribbean were impacted by Hurricane Allen. Some were impacted, for instance, by Hurricane Gilbert in 1986. More recently, we've seen other mortality events from climate change and from coral disease. So there's quite a vigorous debate in the literature in the moment about what killed the corals. And it's basically differences of opinion depending on the personal experience that different authors have had. I think that's somewhat of a silly debate, because the issue is not what killed the corals, it's what caused the corals to lose their resilience so that they can no longer absorb recurrent hurricanes. If you think of this trend, which is a population trend in a demographic sense, the decline in this population is because the birth rates or recruitment rates no longer match the mortality rates. So focusing just on what killed the corals is only half of the demographic question. And we also should be looking at issues like recruitment failure and spawning success and alley effects and so on, the reproductive side of the demographic equation. The scale of the phase shift in Jamaica was island-wide, so about 250 kilometers of coastline shifted quite suddenly. These pairs of graphs show the percent coral cover in the late 1970s, when it was typically about 60 to 70%, and again in 1993, 10 years after the die-off of diadema, when the algal bloom had run its full course. It went through a successional sequence with blue-green algae initially, then green algae, and finally most of the so-called climax species were big species of brown algae, particularly things like Lobophora, Sargassum, and Turbinaria. Anyway, the net result of those algal blooms has been a crash in coral cover. And as I've said earlier, a very similar phase shift with slight variations has occurred now throughout most of the Caribbean over the last 20 years. What's happening more recently? We're beginning to see now in the literature papers that are describing the recovery of diadema. And certainly there are more diadema around today than immediately after the die-off. That's what this graph shows. This is an unpublished meta-analysis that I've done of all the published and grey literature data on diadema densities that I could find from 1970 up to the present. So each of those dots is a study done at a specific location and depth. There are about 2,000 dots on that picture, but many of them are superimposed on each other. I've cut it off at 30 per square meter, but there are about 12 pre-die-off estimates that are higher than that. And I mentioned San Marcos one of 77 from 1976. So the average density of diadema across all depths prior to 1983-84 was about 10 per square meter. For about a decade after the die-off, nobody could find very many, and we're now beginning to see reports in the published and grey literature of more and more diadema. But we're still a long way from these much higher abundances before the die-off occurred. What you can't see in this graph is how many of these dots, particularly after 1983, are on the x-axis. And the answer is about 90% of them. So many places still have no diadema. And what some people, I think, are doing is they're measuring the abundance of diadema where they have recovered and aggregated, rather than the abundance of diadema at more of a landscape scale. That data shows diadema densities at all depths, but there is an interesting difference now in the depth distribution of diadema compared to beforehand. And that's shown here. So this is the same data, except now I've plotted density against depth for 199 studies that predate the die-off, and for 295 more recent estimates in the last 5 years or so. So this is where the diadema are now, at those sorts of densities on average, and this is where they used to be. So prior to the die-off, there were very high densities in shallow water with a depth gradient that extended into quite deep water, into 20 meters and beyond. A lot of people want the diadema to come back because they want herbivory to be reintroduced. I've argued that that's not necessarily the best solution, that it would be better to reintroduce herbivorous fish because of the danger of hyperabundances of diadema reestablishing themselves in the continued absence of their predators, leading to more erosion. The worst possible scenario is that diadema will recover at this depth range where the Acropora palmata used to be, and it will preclude palmata from coming back. And if it only stays in that narrow depth range, then we'll still be left with a regime shift over the vast majority of the reef. I should point out that these depth categories are quite narrow in shallow water, but they're much broader down here. So 80% of the reef is in this direction, and a much smaller amount is in shallow water. Acropora palmata and Acropora cervicornis, by the way, have declined by so much in abundance throughout the Caribbean that they're now considered to be endangered species. They used to be this spatial dominance over a depth range of 2 to 20 meters when I began studying them 30 years ago. All right, to summarize all that up, Jamaican reefs are characterized by very low species redundancies within functional groups. What do I mean by that? Well, if we look at the herbivores, prior to the die-off, there was only one remaining major herbivore because of overfishing of herbivorous fish, and that now is rare, and it's still rare. There were also only 2 branching species of Acropora in the Caribbean, Acropora palmata and Acropora cervicornis, and now those 2 species are endangered. So this is a very altered system, and we can summarize it as follows. The megafauna is long gone, turtles, manatees, and so on. Fish are heavily overfished. There's been a phase shift to algae 25 years ago or more that has persisted, and the remnant corals, which are now only a couple of percentile in cover, are being further suppressed by climate change and disease. Now, this is a very depressing story, but I think it's fair to say that it has been very influential, particularly on coral reef managers around the world, because it tells us what can go wrong. And it also revealed some of the processes, particularly herbivory and recruitment failure and trophic cascades, that are critically important in terms of managing the resilience of coral reefs. So I want to switch now to discuss the Great Barrier Reef in Australia. The Great Barrier Reef is certainly not pristine, but relatively speaking, it's in much better shape than many reefs around the world. We know that runoff into the reef increased from about 1985, beginning with the arrival of about 1 million cattle into the catchment of the Great Barrier Reef. That information comes from coral banding studies, where you can take a core through a long-lived coral, you can date the growth bands in it, and you can look at the chemistry of the band that was laid down, we'll say, in 1830 to 31, and compare that with the band laid down between 1850 and 51, and so on. And we can see a spike in nutrient addition that began with the land clearing and stocking of the Great Barrier Reef catchment in the early colonial period. The early colonial period also saw the beginnings of many new industrial-scale export fisheries. So a long time ago, most of these species were really hammered. Pearl oysters and sea cucumbers were the first Great Barrier Reef fishery, and they both collapsed from overfishing a century ago. About 3 million crocodiles were shot across northern Australia in the 50s and 60s. Dugongs on the southern two-thirds of the Great Barrier Reef have declined by 98% in the last 30 years. Turtles have declined by about 75% for loggerhead. And reef fish have also been depleted. I haven't time to show you the data for that. Some of it is published. So I'll just show you some data by a colleague of mine, Gary Russ, and his students, who's looked at the impact of the hook and line fishery, which is a mixed commercial and recreational fishery, on various species of targeted predatory fish, particularly this one. This is the coral trout, which is a serranid, a grouper, and it's a favorite fish both of commercial fisheries and recreational fishers. Gary and his team have gone to several locations, and this shows two, the Whitsunday Islands and the Palm Islands, which are part of the Great Barrier Reef. And he's looked at the biomass of these targeted species inside and outside no-take areas. And this is actually color-coded because on the zoning maps that the Great Barrier Reef Marine Park Authority produces, these are called green zones, where you can't go fishing, and the blue zones are where you can. And wherever Gary and his team have looked, they have found typically 3 to 5 times more fish and bigger fish inside the no-take areas. No-take areas, by the way, until 2004, comprised 5% of the Great Barrier Reef Marine Park. The other 95% was these blue areas. So there's quite strong evidence for quite a significant decrease in the biomass of targeted fish, even on the Great Barrier Reef, which is a relatively lightly fished environment. As a consequence of this difference in biomass, there have also been some food web changes. So if you take away a top predator like the coral trout, you might predict that there'll be a corresponding shift in the abundance of its prey. And in fact, that's the case. So this is sort of a mirror image of that last graph I showed you. This is data for these two species of damselfish, Pomacentrus, just the coral trout again. And we see the opposite pattern of before. Inside the green no fishing zones, we have fewer prey fish of the targeted predators. So even on the Great Barrier Reef, we can see the beginnings of the sort of trophic shift that in Jamaica led to the release of sea urchins following the demise of their predators and competitors. Another issue for the Great Barrier Reef is runoff, which is sometimes called a bottom-up effect because of the way it propagates upwards through the food chain. This is a historical photo taken in 1890, and when I first saw this picture recently, I was absolutely amazed by it because this is corals that are acropora dominated, branching coral dominated, that are growing on the mainland of Australia. They're growing on the beach. Today, I've never seen an assemblage like that inshore. It looks to my eye much more like a mid-shelf assemblage of today that you would typically find 20 or 30 or 40 kilometers offshore. And I can identify these species, and I've never seen them this close to shore. We can actually go back to this place. If you look at that curvature of the hills in the background, this is the same place today. And that's more typical of what inshore environments look like today. There are mud flats, there's seagrass beds, or whatever, but they're certainly not coral-dominated. We can actually collect these dead corals and age them. My colleague John Pandolfi has done exactly that. Many of these reefs died 50 to 100 years ago at the time when massive land clearing was occurring in the Barrier Reef catchment. Here's some data which is a little bit controversial, which shows coral cover on the Great Barrier Reef using old data gathered by coral reef ecologists between 1960 and 1980, and using more modern data after 2000. Both of these graphs show the percent of reefs that were censused during those two periods that had these categories of coral cover. So if we look at the older data, a lot of reefs, more than half of them, had between 40 and 50% cover, and some had more, and relatively few, less than 20%, had small amounts of cover of 10% or less. The modern data is quite different. It shows that today, more than half of reefs have less than 10% cover, and very few reefs have as much as 40 or above compared to before. Now, there are issues with that comparison. You could argue it's an apple and oranges comparison because this is a real mix of methods: quadrats, transects, belt transects, photographs. And this is a modern monitoring program undertaken by the Australian Institute of Marine Science using a standardized but different set of techniques. However, I think this probably is real to some extent because the people who collected this data were no fools. They're an earlier generation of coral reef ecologists, and I think they probably recorded what they saw. Okay, so to summarize the Great Barrier Reef then, in contrast to Jamaica, we've got a lot more functional redundancy within groups. In particular, there are a lot of herbivorous fish on the Great Barrier Reef, and there is no commercial, recreational, or subsistence fishery for herbivorous fish on the Great Barrier Reef. As well, in contrast to only 2 branching corals in the Caribbean, both of which are now severely depleted, there are 35 species of branching corals on the Great Barrier Reef. However, the megafauna on the Barrier Reef is rapidly declining. The reefs are moderately overfished, nothing like the very heavy fishing of Jamaica. There's some evidence from historical photos and other data that coral cover is declining. And increasingly, the resilience of the reef is being challenged by outbreaks of crown-of-thorns starfish and by climate change. People have argued, by the way, that these crown-of-thorn outbreaks could be the result of a trophic cascade because of fishing of its predators, or it could be a bottom-up effect. Added nutrients means that the larvae of the crown-of-thorns have more planktonic food, phytoplankton, to feed so that more of them survive during the larval phase, resulting in population explosions. Either way, it's apparent that the multiple outbreaks of crown-of-thorns we've seen over the last 30 years are not sustainable. It must be something new, because if it was happening for the last 10,000 years, there wouldn't be much of a reef. So like the trophic cascade of the diadema, they are a cause of concern. So because Australia is a wealthy country, it has the relative luxury of being able to heavily invest in management and reef science infrastructure. And so in the last few years, we've seen a ramping up of the intensity of management of the Great Barrier Reef. So a scaling up, and I think that scaling up has been based on an improved understanding. To some extent, it was informed by the Caribbean crash. And so in 2004, the Great Barrier Reef was rezoned. And so the no-take areas, which formerly had been just 5% of the marine park, are now 33%. And that rezoning was based on an attempt to maintain the ecological function and resilience of the reef in anticipation of future bleaching events. Another management initiative is a new 10-year plan with targets for the reduction of nutrient and sediment loads in rivers that are running off into the Great Barrier Reef Lagoon. A major challenge, though, for the Great Barrier Reef is developing new metrics that monitor resilience. How do you do that? At the moment, when we want to monitor the health of a coral reef, we go and count things. We count crown-of-thorn starfish, we count coral cover, we count coral trout. Ideally, though, we should be looking at resilience and thresholds and feedbacks and drivers. In other words, the dynamics of the regime shift that could potentially occur between coral dominance and dominance by something else that we don't want. So if I could make an analogy that this is our coral reef ecosystem, at some distance downstream, there's a huge thundering waterfall that we don't want to go over. We've got some limited capacity to navigate this system by paddling upstream. So in order to understand its dynamics, we'd want to know something about the drivers. How quickly or slowly is that stream moving towards a threshold? And what's the distance to that threshold? But we never measure those sorts of dynamics. Instead, what we do is count the number of people in the boat. And that's not terribly useful. The final case study I want to deal with today is a new one for us, and it's the information I'll describe now is based on a workshop that Bob Stenick and I convened last summer in Maine. And we developed with our colleagues a concept which we've called the Gilded Traps. The Gulf of Maine is an interesting system because it's relatively simple compared to tropical systems. There aren't that many species. It's low biodiversity. And so the sorts of serial depletion of fisheries and the trophic cascades that have resulted from that are very clear. So Maine is characterized by a sequence of sequential boom and bust fisheries, a very famous one, of course, being the cod, which has recently collapsed. So this system illustrates multiple trophic cascades, and in fact, some of those cascades have resulted in new fisheries, which I've called emergent fisheries. Now, in Jamaica, nobody fished for diadema, and in Australia, no one fishes for crown of thorns starfish, and nobody fishes for seaweed, to speak of. But in Maine, new species that were formerly quite rare, including sea urchins and lobsters, have boomed in the absence of their predators, and they are economically very lucrative regime shifts. We've also seen in Maine a loss of biodiversity and a loss of economic options. I'll show you some data on that in a moment. So now we have over-reliance on one remaining great fishery, namely the fishery for lobsters. So we have a situation that is economically very successful. The lobstermen are making a lot of money, but it's the result of huge ecological shifts, and in fact, I'm going to argue it's an ecological disaster in waiting. So no one could predict before the regime shift in Jamaica that it was going to happen. But I think we're now getting to the stage where we understand enough of the dynamics of these systems that we actually can make reasonable predictions. This situation is also socially very brittle because if the next predicted regime shift occurs, it's going to have huge economic and social consequences. And I'll describe those in just a moment. So just some pictures showing the sort of depletion that has taken place over time. If you look at old photographs of wharves and fish markets and proud fishermen and so on, you'll see these monster fish of species that are no longer commercially viable. We've also seen in Maine trophic cascades that result in emergent fisheries. This is a sea urchin barren that I mentioned at the beginning of the talk. These population explosions of sea urchins are very much analogous to what happened to diadema in the Caribbean in the absence of its predators. The sea urchin has eaten away the kelp beds, which are the normal dominant plant assemblage in this system. These very high densities of sea urchins are prone to disease outbreaks, and in fact in Canada and in Nova Scotia, that's exactly what we've seen. Epidemics of temperate water sea urchin diseases following release from predation due to overfishing of their predators. In Maine, however, this boom of sea urchins supported a new fishery, and it was an export fishery of uni, which is sea urchin roe, for the Japanese sushi market. That fishery lasted about 10 years before it collapsed. Another trophic cascade is the emergence of lobsters. Big bottom-dwelling fish, so-called ground fish, like cod, are now ecologically extinct in this system, and as a consequence, their lobster prey has undergone a population explosion. So that's very lucrative economically, but ecologically, it's a consequence of severe ecosystem degradation and distortion of food webs. Here's some data that shows you the population explosion of lobsters through time. This is data from 1925 up to the present. The black curve is the landings of lobsters in metric tons. And in 2004, 28,000 metric tons of lobsters, that's a lot of lobsters, was landed by 7,000 lobster fishers in the Gulf of Maine. And the blue trajectory here is the number of traps that those lobstermen deploy each season. There are now 3 million traps in the Gulf of Maine. That's 3 per person for every man, woman, and child. So this is a huge, huge fishery. And if you wander along the coastline, you can see these traps in storage outside the fishing season. They're quite large. They've got a footprint of about 2 square meters. The bait for these traps is a fishery in itself. It's a pelagic herring species. And so the fishermen are providing 80% of the diet of wild lobsters by baiting these traps. The lobsters come and go into the traps. It's a game of Russian roulette. You lose if the trap is lifted before you've finished eating your herring. But it's basically an artificial trophic link between a pelagic fish and a benthic scavenger on a scale that I've never seen in any other marine system. If you look out on the water, the density of the lobster traps is so huge that it would actually physically preclude any other fishery. You couldn't pull a net through this, assuming there were actually anything else in the water to fish. I counted the buoys in this photograph. There's 42 of them. Each one of them is attached with a rope to one or more lobster traps. The density of lobsters on the bottom for hundreds of kilometers is between 1 and 2 lobsters per square meter. So an enormous population explosion, just like the diadem explosion and the temperate sea urchin explosion that I showed you a moment ago. The lobsters, in the absence of predators, have also shifted habitats. So these traps are actually in relatively shallow water on muddy bottoms. No self-respecting lobster, when there were predators present, would be found there because of the risk of predation and also the lack of food. The lack of food's not a problem anymore because the fishing traps actually supply it. So this is a wild fishery that's really more akin to ranching or aquaculture in its scale and mode of operation. Here's some data on the economic value of 23 fisheries in the Gulf of Maine from 1950 up to the present. And I just want to point out a couple of species. The blue is lobsters, and it is now the mainstay of landing earnings in this system. The green is sea urchins. That fishery didn't exist before 1990. It boomed and then it busted. You can actually calculate a diversity index of these earnings, and that's what this black trajectory shows here. So this is diversity of earnings from landings through time from 1950 up to 2005. The diversity of value of species actually went up from the 60s to about 1990. And that was because following the collapse of coastal cod, the fishers targeted a range of other species that they hadn't looked at before, and so diversity went up. But they were quickly exhausted, and so from 1990 to the present, the diversity of earnings from landings has crashed. One on this is a Shannon Index that community ecologists will be very familiar with. One on this index means that there's no diversity, that it's all entirely attributable to one species. So this blue line is the proportion of the earnings attributable to one species, namely the lobster. And right now, it's just above 80%. We would argue that this is a system that's incredibly perilous. It's a disaster waiting to happen because of the unnaturally high densities of lobsters at 1 to 2 per square meter. There are tens of millions of lobsters in the Gulf of Maine in unnaturally close proximity, and it seems only a matter of time before that unnaturally high density will result in a disease epidemic. And in fact, it may already have started. So in Rhode Island, which has a lobster fishery for this same species, a few hundred kilometers south of the Gulf of Maine, in the late 1990s, 72% of the lobster population died because of this shell disease, which generally attacks most intensely the older lobsters that molt relatively infrequently. This is a younger lobster, and as you can see, it doesn't look terribly appetizing. If this disease struck the Gulf of Maine, it would be economically devastating because over time there's been a gradual erosion of biodiversity, a gradual erosion of economic options, and this is the last game in town. And if it goes, then the whole system will collapse. We think that this system is also socially very brittle because many of the fishers are in debt, borrowing money for bigger and bigger boats because they've never caught so many lobsters before in their career. They might as well get a bigger boat and more traps, and so on. But because they're in debt, if the season fails even for 1 year, they may well have to sell their coastal property, which is now incredibly valuable because of gentrification. So this is a summer home or a retiree home. It's worth a few $1 million, and this real estate is in short supply. So we think socially this system is very vulnerable to what we think is almost the inevitable outbreak of disease. So this is our Gilded Trap. Basically, it's a regime shift to an undesirable state with a very deep basin. It's highly resilient. Currently, we're at a lobster monoculture. We've lost a lot of diversity. So we had formerly a mixed fishery that was robust for centuries. But with the intensification and mechanization of fisheries, we saw declining economic options, declining biodiversity, leading to this current very vulnerable situation. And if the disease epidemic comes, as we're predicting, we'll be in a very deep, highly resilient basin that is totally undesirable. It's a gilded trap, a gold-plated trap, because this is incredibly lucrative. So there are no incentives financially to change and escape from this gilded trap. And so my final slide is about escaping from the gilded trap. What could we do? Well, I think an important issue is supporting an appropriate framework for adaptive governance that has shared responsibilities and that operates at multiple scales, both locally, at the state level, and regionally. We need to build a shared understanding of resource and ecosystem dynamics to better inform repairing food webs, rebuilding diversity, rebuilding economic options into this system. And we need to change the current focus from single-species fisheries models. Those single-species fisheries models tell us that the lobster fishery is a huge success. I would argue that it isn't. And we need to change from that mindset to undertaking proactive management of ecosystems, anticipating future uncertainty like climate change and the lobster disease, aimed at rebuilding social and ecological resilience before the gilded trap becomes permanent. Thank you very much.
Thank you very much, Terry.
economic options. And I'm wondering if that's kind of true, because if this business is so lucrative that people are having so much money, I mean, isn't the sort of transformative capacity of the system in terms of being able to shift your investments into something else also bigger? But you might choose not to diversify economically at the moment because it's so lucrative.
Yeah, there's an interesting generational pattern. You compare the attitudes and behavior of older and younger fishers. The older fishers have seen other fisheries come and go. They've seen the boom and busts, and they've experienced at first hand some of the hardships of their stock collapsing in front of their eyes and having to re-gear and retool to target some other fishery. The younger guys have only experienced the good times, and in the last couple of decades, they've only got better and better. So those are probably the most vulnerable people in that they're heavily in debt. And the older guys have tended to diversify their income options. So that picture I showed you of the traps among the houses, some of those houses are getting supplementary income from tourism. Some of them are guest houses, for instance. Others are small cafes. There's also a sort of niche commercialization enterprise in selling local art. So I think some people are aware of the vulnerability of this system, but many people aren't.
Thinking about the clam fishery, the main clam fishery, is it gone as well?
The clam fishery in Maine? No, it's still there. It's the second most valuable one by income. So lobster is currently 80%, clams is 4%, and the next 5 species with clams make up only 10.
Another question. If you manage to stop the lobster fishery in Maine, will the other sort of species come back in the system?
No.
No?
No. If the lobsters die off, it's not going to promote the recovery of their predators. It'll just be an empty system with no fishery left. That's right. So one option would be to purposely fish down the lobsters to get them away from dangerously high, disease-prone population densities. One of the ironies of this situation is that the groundfish predators are a bycatch in the lobster traps. So it would make sense for that bycatch to be released, but usually it isn't. Yep.
Something unusual, or would it occur in every ecosystem? And what about our ability to predict it?
Well, I've argued elsewhere that the vulnerability of systems to regime shifts is often a function of their diversity, and other people in the room have made similar arguments. So I emphasize the biodiversity of these different systems because of the role, the functional role that different species have. So in Jamaica, the loss of herbivorous fish didn't matter for a while because something else could substitute for it, namely sea urchins. But that was a very vulnerable system. So I think part of the reason why the Gulf of Maine is so dynamic and so vulnerable to recurrent regime shifts, leading now to the ultimate one, is because it's a relatively depauperate and simple system. Hello?
Is there a forum in Maine where these results from your research could be disseminated to reach the fishers, and they would, where they would listen and where they would?
Yeah, there are two. The last study I described from Maine was based on a week-long workshop that we held in Maine, and the local organizers of that workshop were Bob Stenick and Jim Wilson. Bob's a marine ecologist, and Jim is a fisheries economist. And those two individuals have spent many years meeting with various players in this system, the fishermen, the management agencies at various levels, trying to get across the complexity of this message. So yes, that is happening. Hello.
I understand the idea that to continue fishing the lobsters is probably going to collapse, but if you want to make it more sustainable, wouldn't you have to reduce it by an enormous amount anyway? So it has to be, I agree with your point, but for the fishers, this just the choice between reducing it 80%, maybe, I don't know the figures, but reducing it a lot, or wait a couple of years and having the same economic collapse, or I don't know if it's, you see what I'm trying to say? There's not many options left. The dug themselves into a hole.
That's right. Yeah, a very lucrative hole at the moment, but it's an incredibly dangerous place right now.
So what's the likelihood of, what are the possibilities of setting up that governance system, as you're suggesting? The barrier reef case has obviously been a huge success. What are the institutions or the authorities in Maine set up to, or are they open to this kind of idea to set up a similar system?
I think the truthful answer is no. They're not. The local governance is sometimes very strong. So we met with fishermen and fishermen groups on several occasions, and at that sort of scale of management, some of them are incredibly well organized. So the fisheries co-op we were engaging with has decided to close their fishery seasonally, whereas many other cooperatives fish throughout the year. So they collectively made the decision to only fish for lobsters in the dead of winter when the price is highest, and to close their fishery for the rest of the year to allow the stocks to rebuild. They also won't go fishing on the first declared day of the fishery if somebody's boat in the co-op isn't ready. They'll wait so that they can all go together. And this year they bought a new fisher, a woman, a house, so that she could be recruited into their fisheries co-op. She couldn't have afforded a house because of gentrification, so the lobster co-op bought one for her. So there's at that scale, there's a lot of cooperation. That particular co-op have also instigated what's called a slot fishery. So they have holes in the traps that allow juveniles to escape, and they don't collect lobster above a certain maximum size. They only collect a portion of the population that's medium-sized. That allows the juveniles to grow up and the larger ones to be retained as the brood stock. So at that level, they're quite well organized, although it's patchy from co-op to co-op. At the state scale and above, though, it's a bit of a bureaucratic nightmare. And the mindset is still very much, let's manage these fisheries species by species by calculating maximum sustainable yield and pay no attention to who's eating whom or why this is booming and that's going through a crash. That's probably the main obstacle to a better governance system.
I think it's interesting this case that Terry just gave us, because it has been described in several parts of the literature on the social side as one of the key success stories of local management of resources. And it really illustrates the need to look at this as unified or integrated systems, the ecological and the social together. Similarly, if you only look at the ecological part, you may draw other conclusions about how it works, but misses the social point. So I think this case is a really good example of showing that these feedbacks are actually between, not just occasionally between the system, question and then we get some round off.
Yes. We have the Baltic Sea very close to here, and some are thinking that it's a phase shift going on in the Baltic Sea. Do you have any comments or knowledge about these things?
I know a little bit what I've read about it. It seems to me to be somewhat similar to the Great Barrier Reef in that the food web is greatly distorted from the top, but there's also the issue of runoff of nutrients. So I hope I didn't infer that those were alternative stressors on ecosystems in many places, including, I think, the Baltic. Those are occurring simultaneously. I read an interesting paper recently about historical reconstruction of the Baltic food web. Historically, it would have been completely different, with big populations of predatory fish that are now largely absent.
Okay, thank you very much for taking your time and giving this lecture to us.
Thank you.
Thank you.